Transition state theory was one of the most difficult physical chemistry concepts for me to understand. Since transition states cannot be observed, there are a lot of assumptions, manipulating equations, and contriving variables involved in reaching an equation that makes sense and has variables that can be measured in the lab. The equation we derive relates the rate constant K of a reaction to the free energy of the transition state. This is not the activation energy, as in the Arrhenius equation. Activation energy is the difference between the free energy of the reactants and the transition state. Transition state theory wants to look at the absolute free energy of the transition state. To help myself understand this topic, I went back through the lecture slides and took a more careful look at each equation and probed each assumption and manipulation used to give the final equation. I realized that my real stumbling block came from the derivation of big K in this equation, where the rate of the reaction overall is equal to the product of the formation of activated complex rate and the consumption of activated complex. Ultimately, what helped me understand it was the Wikipedia article on transition state theory, as well as reminding myself about Boltzmann distributions and equilibrium constants and their derivations. The first assumption says that big K double dagger can be treated as an equilibrium constant. It must still be related to measurable quantities, however, and we can't measure the concentration of the activated complex. As an equilibrium constant, big K can be related to the delta G of transition without much fuss by rearranging the Gibbs energy equilibrium equation. This gives this equation. Now, notice I've drawn big K as a prime because this isn't a true equilibrium with reactants and products. The final touch to yield an accurate description of big K is to include temperature-dependent statistical mechanical treatment. This is done because only a small portion of the population of reactants can even reach transition state energy as described by a Boltzmann distribution. Thus, Boltzmann's constant is included in the equation. Interestingly, the molecular vibrational frequency term nu is included in the bottom of this equation since it leads to the formation of reactants in the equilibrium described by big K. This means that when big K and little k's equations are combined, the frequency term disappears altogether. This makes sense because random vibrations are nearly equally likely to form products as they are to form reactants from the activated complex AB transition state.